Okay. Um, so the lesson today is going to involve the second derivative of a function. And as in terms of how you get it, you're really just repeating, you're literally repeating what you've been doing already. So when you've been taking a derivative as you have been all semester long, that's also referred to as the first derivative. You just go through a differentiation process once. But sometimes there's a need for the second derivative, so you take the derivative like you have been doing, and then just take a derivative of that. So you're going through the whole differentiation process twice. And today we're going to see problems in which you take the second derivative and work with it, and also how you interpret it. In recent lessons, we've seen how the first derivative can tell you if a function is um, increasing or decreasing, and also when it's equal to, so according to whether it's positive or negative, and when it's equal to zero, how that may be um, a maximum or minimum. The second derivative also has its interpretation. So about the shape of a graph of a function. So when the second derivative is positive or negative, its graph is concave up or concave down, and I will show you a graph of what that means. And when the second derivative is equal to zero, that may mean what is called an inflection point, which is a statement about how the uh, function is changing, and how rapidly it's changing. All right. Um, so first, we're just going to be dealing with the basics of the second derivative. So we have this function here, and the first step is find f double prime of x. So notice the notation here. You're accustomed to seeing f prime of x, so a single apostrophe for the derivative, which I'll refer to as a first derivative. And here we have f double prime, so two apostrophes for second derivative. And I'm emphasizing this because it happens so often in problems where if you have to compute the derivative in some cases, second derivative in others, um, that students get wrong which derivative is being asked for. So please pay attention to that, which derivative is actually required. So you don't want to throw away points on something like that. So for this case, all right, so here's our original function. So we go ahead and take its derivative, f prime, which is its first derivative, in the usual way, just using the power rule on each term. So then, for second derivative, I'm just going to take a derivative again of this. So the steps are exactly the same. So we pull the 2 down and we get minus 48x. And then here we apply the coefficient rule and get 12. So you're just going through the same process twice. And that is the second derivative. And then for the second step, it's asking for the value of a second derivative at select points. So x equals 1, x equals 5, x equals 7. So that is nothing more than plug and chug. Although I will point out that you'll see problems like this, like on the second test, it may happen on the final also, where you're just asked to evaluate the second derivative at certain points, and it's really surprising how often students get these wrong, even if they do this part right and get the correct second derivative, then it's just a matter of plugging in certain x values and making mistakes at that point. So, it's something to be careful about. So here we're just setting x equal 1 and grinding these out, and then same process for x equal 5 and x equals 7. Now, since these problems come in 2 steps, like on a test, what I will try to do is suppose you get the wrong second derivative in step 1, and of course you're going to lose credit for that, although you may get partial credit. But whatever you take here, whatever answer you get, if you at least do the substitution process right, so you get the correct values of when you plug in the stated x's, if this substitution process is performed correctly, then that's something that I can give you credit for. Okay. So the next problem is where we work with how the second derivative is interpreted. So here you're given this function and what is asked for. Okay, what's a new page? What is asked for is wait, seems like something is missing here. There should be it's a step 1 of 2, therefore there should be a second step. Let me take a look at that. Oh, points of inflection. Okay. All right. Yes, there's a second step. Let me fill that in real quick. Okay. So intervals in which a function is concave upwards or concave downwards. This is very similar to problems you've had recently where you have to determine whether a function is increasing or decreasing. And in that case, in those problems, you were for finding out whether the first derivative was positive or negative. Here we're trying to see whether the second derivative is positive or negative. So what we have here is, so the graph is concave upward if the second derivative is positive, concave downward if negative, and then a point of inflection might occur when it's equal to 0, just as the function might have a maximum or minimum when the first derivative is 0. Okay. So first we'll go for a process of getting a second derivative. Okay, so working with this function. So we go ahead for the usual process of applying a power rule to get to this point, and then the coefficient rule just gives us -12. Now, when you have a polynomial like this, taking a derivative reduces the degree by 1. So here we have a quadratic. Taking a second derivative reduces the degree by 2. So we're down to just a constant, a polynomial degree 0. Just as the derivative of a constant, the second derivative of a linear function is 0. So notice this term here, 4x plus 3, these terms made no contribution at all to the second derivative. Now here we see that the second derivative is a constant, it's negative. So that means that the function is always concave downward. So what you would enter for an answer is this interval for concave downward, and then it's not concave. It's not concave upward anywhere. Okay. So what do you do is you would select. Make a note of that. Okay. So as far as answer, you'd enter none for concave upward. The second step is locate any points of inflection. So in this case, because f double prime Whoops. Is never 0. It's always equal to minus 12. And there aren't any. So there again, you would enter none in Hawks. Okay. Here, same kind of problem. Find where it's concave up or concave down by second derivative being positive or negative. And then we'll see if it's equal to 0 anywhere to find a point of inflection. So in this case, there should be one. So applying the same power rule as usual. To get the first derivative, then apply the power rule again here to get the second derivative. And now what we need to do is see where this is equal to 0 to try to sort out where the function is concave up or down and whether there might be a point of inflection or an inflection point. All right. So you go ahead and take the second derivative and set that equal to 0. And so what would x be? So what is the solution to this?
-8.
Yes. So go ahead and move 9 and 6 to the other side, divide by minus 12, and we get -8. So that's a one possibility for an inflection point. Okay. It's weird that after answering a question and then remuting yourself. I don't know if anyone else can hear. There's still background noise. It's kind of strange, but I've seen this regularly in Teams how it does that. Okay, so what is a point of inflection? How do we know if it's a point of inflection? I said there might be one here. How do we know? If a concavity changes, so if a function changes from concave up to concave down at a certain point, in this case possibly x equal -8, then that would be an inflection point. So what you do is you check on either side of -8. So you pick x values on either side and plug them into the second derivative to see if it's positive or negative. It's on a new page. Okay. So first we check x less than -8. And you can pick any x value. For example, choosing x equal to -10. So we can just plug that into the second derivative that we just got. And here we get a positive value. So it's concave upward on the left to the left of -8. Then you pick another x value. Again, you pick anything greater than -8, so -6. And we get a negative value. So there is a change in concavity from concave upward to concave downward, so from plus to minus. Any change in sign qualifies. So you specify this interval for concave upward, this interval for concave downward. So that's for in the first part of the problem. And then points of inflection. So because we have a change in concavity from up to down, then we can say that x equal -8 is an inflection point. Now, once the answer is an xy pair, so x will be -8. To get y, you substitute -8 into the original function and get your y value that way. Okay, so we just go ahead and grind that out. So your final answer is that x equal minus 8, and then y equal to what we got here, minus 2109. So watch your signs when you're plugging in negative values. Like here we have minus 8 cubed. That's going to be a negative value, but then times minus 2 will give you something positive. Whereas minus 8 squared, that is positive, but then times minus 48 will give you negative. But a lot of sign mistakes happen here. Okay. All right. Now, all right, here we have, it's only asking for a second derivative, not to do anything with it. It's a little bit more of a pain because now we have this radical here. And just like when you would be taking the first derivative, you would need to rewrite the function first. So here we rewrite the fourth root of x as x to the 1/4. And then you can go ahead and take a derivative like you normally would. So here we apply the power rule to both of these terms. So then the 1/4 comes down, and then 1/4 minus 1, that's the same as 1/4 minus 4/4. And thus we get minus 3/4 here. But then the problem asks for a second derivative, so it's necessary to carry this out again. So for the second derivative, the coefficient rule for its first term, and then here the 9/4 stays here. The minus 3/4 comes down, and then we have x to the minus 3/4 minus 1. So you're subtracting 1 from the exponent again. So it's going to be even more negative. So we go ahead and multiply these out, and we get minus 7/4 for the power of x. And that's the final answer for this one. But again, keep track of which derivative is being asked for, so that I mean, I can give partial credit in certain cases, like if it wants a second derivative and your answer turns out to be a first derivative, but there's a chance to get full credit, so don't throw that away. All right. Now here we have a graph. You've had problems like these where a graph is given and you're asked to point out what intervals a function is increasing or decreasing on. Here it's asking for where's the function concave upward or concave downward. So now I need to show you what that looks like. So if so this part of a curve right here, starting from the left and going all the way to this point. So right here we're at x equal to minus 3. This is an example of concave upward. So the graph is so the opening is upward. But here, this graph from minus 3 to 0, that's an example of concave downward. So it's opening down. Here again, from 0 up to 6, that's concave upward again. And then it switches to concave down, starting from x equals 6 all the way to infinity. So you're familiar with parabolas that are facing up or facing down. It's the same idea. So here, if you think of this curve kind of like a part of a parabola, that it's facing up. Here it's facing down, facing up, facing down. So that's how you can tell from a graph concave upward versus concave downward. So what you would do for your answer to this problem is enter the intervals first for concave upward and then for concave downward. So in this case, we have two intervals for so it's concave up. So starting from the left, so that's going to minus infinity all the way up to minus 3. And then the next time is concave upward is starting from x equals 0 to x equals 6. So that's concave up. And then from minus 3 to 0, that's concave down. From 6 onward, so 6 to infinity, that's concave downward. So use this, so again, up, down, use this to keep in mind visually what it means for a function to be concave upward or concave downward. So questions about how the intervals were identified in this case. The other part is determine x coordinates of any inflection points. Now, inflection points are where concavity changes. So since the concavity is up, down, at these 3 points are where concavity changes. So you would just read the x values off of the graph. So minus 3, 0. And then because we have 5 sitting here, it's 1 unit over from that. It's 6. So that's what you would enter like in a comma-separated list of x values. So really what you would enter in Hawks is something like this. Okay. Here's another problem where we're asking for concave up, concave down, and if it changes at all, are there any inflection points? Now, taking a second derivative of this is going to be a pain. We're going to use more advanced differentiation rules than we have up to this point. All right, so first, it's necessary to rewrite this function. How would you rewrite it before taking even the first derivative?
It'd be x squared plus 5 to the 1/2 power.
Yeah, so all of that would be raised to the 1/2. Okay. So now we go ahead and use, well, what rule would you use from this point to take the first derivative? What's that called?
Wouldn't it be like the power rule, but within the chain rule or something?
It is, yes, and that's known as the general power rule. But yes,
Okay.
it is a power rule and chain rule together. Okay, so when we carry that out, the 1/2 comes down. Then we have this as is, raised to the exponent -1. And then you got to take a derivative of what's inside here, and that's where the 16x comes from. Now, if all that was needed was the first derivative, it'd be perfectly fine to stop here. But if you know you're going to take a second derivative, that's what the problem asks for. It's important to try to clean up the first derivative as much as you can. So here I just carry out the 1/2 and the 16 to get 8x up top. And then here we have 8x squared plus 5 to the minus 1/2. And then so then we put that 8x squared plus 5 to 1/2, but in the denominator. Now we take a derivative of this. So that's so what rule would be required for that case?
The product rule? Oh wait.
Quotient.
Quotient.
Quotient rule.
Although I will say that if you wrote this as 8x times 8x squared plus 5 to the minus 1/2, that would be product rule. I actually did have a student.
That's what I was doing. I was doing it on my paper, and I looked up and I was like, okay.
Okay. Well, I can totally understand that. And I did once have a student who insisted that the quotient rule was unnecessary because technically you can always rewrite a quotient as a product. So either way, okay. So written this way, we do the quotient rule. So we have denominator times the derivative of the numerator, which is 8, minus 8x, so the numerator, times the derivative of a denominator. But that was carried out earlier, and then divided by the denominator squared. But the denominator is a square root. So you square that, gets rid of a square root. So you just have 8x squared plus 5 down below. Now, to find where it's concave up or concave down, you want to know where this is equal to 0. And you would focus on the numerator, because only if the numerator is 0, then the whole thing is 0. But this is quite a mess. So we want to try to simplify this in any way we can. And so this is something I've not had to get into before. And thankfully, it's not often necessary. But if this is going to be probably a bit, you'll find this a bit strange, but it works in terms of the overall goal, and that is finding out when this is positive or negative. So what I'm going to do is, okay, well, first a little bit of cleanup. Oh wait, I want to give more room here. Okay, so here all I've done is just I've taken the 8x, the 1/2, and the 16x, and just combined them into one factor here of a 64x squared. Okay, what I'm going to do is, notice here I have 8x squared plus 5 to the plus 1/2, and here I have 8x squared plus 5 to the minus 1/2. When you have a situation like this that typically arises from the product or quotient rule, where you have the same expression, 8x squared plus 5, raised to powers that are 1 apart, like this, plus 1/2, minus 1/2. In terms of simplifying, it's actually quite helpful to factor out 8x squared plus 5 to the lower power, so to the minus 1/2. So that's what I'm going to do here. Now, so what happens when I pull this out? Well, pulling it out of this term is easy. You just write down what's left, a minus 64x squared. Now, factoring out 8x squared plus 5 to the minus 1/2 from this term means I have to add 1/2 to the exponent here to compensate. So what do I get? I get 8x squared plus 5 to the first power. Look at the exponents. I have minus 1/2 and 1. Those added together give me plus 1/2. Another way of thinking about it, if you're not seeing why it works out this way, I'll add a intermediate step. Because You can always think of factoring out as same as multiplying or dividing by something. So what I could do, there's a different way to look at it. If I want to factor out 8x squared plus 5 to be minus 1/2, that's the same as writing down what I want to factor out and then writing down its multiplicative inverse to compensate for it. So going from here to here, what have I actually done? All I've done is put in this. That clearly cancels out because we have to a minus 1/2 to a plus 1/2. Now, this is what I want to factor out. So I'm going to leave it here. This, I will now distribute to everything here. So here I have 8x squared plus 5 to 1/2 and then to 1/2 again. Here I add the exponents and I get 8x squared plus 5. Here, again, I add the exponents. I have plus 1/2 minus 1/2. So I get 8x squared plus 5 to the 0 power, which is 1, which is why this works sitting here. I know this is kind of unusual. Any questions about how this was arrived at? Now, the reason why I did that is now the numerator is a whole lot simpler. In fact, what do we have here? I have 8 times 8x squared. That's 64x squared. Cancels with this 4x squared here. So now the final form of a second derivative is this. And I needed it in this form because of what follows in this question that we need to know. Whether this is positive or negative. And that's pretty hard to do when it's written like this. But here it's quite easy to do. First of all, denominator is always positive because you have something squared here then raised to a power. And the numerator is always positive. So this whole second derivative is always positive. So we can say that the function is always concave up. So for your answer, you'd enter minus infinity to infinity as the interval on which it's concave up. And then for concave down, you would select a none. And then that makes moot the question of okay, so that's the final answer there. For inflection points, it's always concave up. So there aren't going to be any inflection points. So again, you would select none. Okay. Lastly, a word problem. So here we have a function that describes sales as a function of advertising. So if X thousand advertising dollars are spent, it appears to result in this amount in terms of sales, again, in thousands of dollars. And so the advertising budget could be anywhere from $0 to $50,000. So the idea is that one would expect that as you start spending money on advertising, that would drive an increase in sales. But at some point, you find that you're not really gaining that much anymore from additional advertising. So you want to have an idea of when does the tide turn on you, and that's what leads to this notion of the point of diminishing returns. So what does that mean? The diminishing returns is an inflection point at which concavity changes from up to down. Because when a function is concave up, and I'll go back to a graph we had earlier to give you the visual. All right, so here we have a case of a graph being concave up. Here at this point, this stretch here from like around x equal like 2.5 up until 6, it's not just concave up, it is also increasing. And what we see here is it's getting steeper and steeper. Why? Because the function itself is increasing, and the derivative, f prime, first derivative, is not only positive to make it increasing, but it's increasing because its rate of change, which is the second derivative, is also positive. So when you have a function whose first and second derivatives are both positive, the function is increasing more and more rapidly. So we're gaining more and more. In this case, like if these were advertising dollars. So that's good. It's driving sales at an accelerating rate. But then we have this, where the I'm not sure what that flashing red is. It's kind of annoying. That here it changes from concave up to concave down. The function is still increasing. You are still gaining sales from pumping in more advertising dollars, but you're not getting as much. The rate of increase is going down. It's increasing, but more and more slowly. This is an example visually of, this is an illustration of a point of diminishing returns right here at x equals 6, where it changes from concave up to concave down. The tide is turned, that you're no longer, you're still seeing some gains, but not as much. And you're approaching a point at which you may start to have sales go down if you're not careful. Maybe people are sick of seeing your stupid ads. Okay, so that's what we want to find with this function. At what point does the second derivative change from positive to negative? So that means finding out where, if anywhere, the second derivative is equal to 0. So then we go ahead and take a second derivative. All right, so first, here we get nothing from here, and then applying a power rule as usual to get first derivative, and then 45 minus 1.8x, that's the second derivative. So then you go ahead and set that equal to 0. And just carry out the algebra, and we find that when x is 25, so when you've put in $25 on advertising, that appears that may be an inflection point. You have to make sure though. So you check for x less than and greater than 25. You try values in the second derivative. So here we're just arbitrarily picking 10, and we see, okay, it's concave up when x is less than 25. So at that point, we're seeing an acceleration due to more advertising. Then you check x greater than 25. Does it go negative? And sure enough, it does. So what happens here is we have a change from concave up to concave down. So x equals 25 really is the point of diminishing returns. But what it asks for is not just the x value, not just the advertising budget for point of diminishing returns, but also what were your sales at that point. So if we go back to the original question, Enter the amount spent on advertising as well as the sales in dollars. The amount spent on advertising, look at how a function is defined. X is thousands of dollars spent on advertising. So $25,000 is that amount spent. And then the sales in dollars. Look at the function. S is in thousands of dollars. So make sure to check your units so that the number you input is the right one. So what you do is, now we take x equal 25, substitute that into the function. And what we get is 9524. So keep in mind that is thousands of dollars. So what the conclusion is 25,000 is how much was spent on advertising, and then this amount, so 9 million plus, that is how much in dollars was raked in sales. So what you would find is, if you bump this up to 26, 27, you probably still see more sales, but there'd be less of a gain than before, and that would just keep tailing off until you might not be gaining anything. In fact, if I look back at the first derivative and see where that may be equal to 0. Oh, actually, yeah, this is equal to 0 when x is either 0 or 50. So right at the upper bound, x being 50, is where there would no longer be any gain in sales from continued advertising. All right, so keep in mind, when it asks for point of diminishing returns, that's when we have an inflection point. Concavity is changing from up to down. Okay, so questions on any of these problems?
What did the coordinate actually end up being for the point of inflection?
I'm sorry, what?
Oh, I was going to say, what is the actual coordinate for the point of inflection? Would it be like 25 and then 9,524?
Yeah, so if it asks for it as a point, like a point on the graph, yes, it would be those. Okay. And that's what asks for in many other problems. But here, since it wanted these amounts on dollars, that's why it was necessary to convert.
Oh, okay. What was I might have missed that. What was the amount that was spent on advertising?
Oh, okay. Well, it's 20. So x is 25.
Okay.
But then 25,000 is, yeah. So here, a dollar.
Oh, gotcha. Okay. Thank you.
Okay. Other questions? Okay, so we still have a few more lessons coming up. So next week, 4.2 and 4.4, then following week, 4.5 in review. So the second test, let me check here. Okay, on Friday, October 30th. So still a while yet. So 3 weeks from tomorrow is when the second test is due. The practice test is out there already. So be sure as we get closer to make use of that. And that'll be only ever test until the final. Okay, so I will end the recording at this point, and then anyone who still has questions is welcome to stick around. Otherwise, you may all scram, all 7 of you.